Hey, deep divers, ever wonder what the universe is hiding? Like what truly mind-blowing particles might be out there just waiting to be discovered?
It's like we're searching for something incredibly rare.
Well, today we are diving deep into the world of cutting-edge physics. We're going to explore how scientists are using something called graph neural networks to track down these cosmic mysteries.
It really is like searching for a rare flower, let's say in the Amazon
Yeah,
rainforest.
okay.
But instead of a flower, we're talking about particles so rare, so bizarre that they could rewrite our understanding of physics as we know it.
Well, okay, so we're not talking about your everyday electrons and protons here.
No, no.
We're talking about going beyond the standard model,
Yeah.
right? Uncharted territory.
Yes.
But before we get ahead of ourselves, what exactly are we dealing with in this research?
Now imagine the Large Hadron Collider smashing protons together at nearly the speed of light. These collisions create just a shower of particles, kind of like a subatomic fireworks display.
Okay, I'm picturing it.
Good.
So how do we find anything useful in that chaotic mess?
Well, physicists are particularly interested in something called boosted jets.
Okay.
These are like concentrated bursts of particles. Think of them as little particle packs that might hold the key to uncovering new physics.
Particle packs, I like that.
Hmm.
But how do these graph neural networks, or GNNs, help us make sense of these jets?
Okay, so think of a GNN as a detective with a special talent for analyzing relationships.
Okay,
In this case, they're looking at the relationships between the particles within each boosted jet.
got it.
Each particle becomes like a dot on a map, a node, and the lines between them, the edges, represent their connections, their energy, momentum, how they're all related.
So it's not just about identifying the individual particles, but understanding how they interact as a group,
Yes,
like a cosmic social network.
exactly.
And that's where the real detective work begins, right?
Exactly. The type of GNN used here is called an autoencoder.
Okay,
Imagine showing a computer thousands of pictures of cats.
right.
Eventually, it learns to recognize what makes a cat a cat.
So it builds up this mental image, a template of what to expect.
Precisely. Now, show that computer a picture of, say, a dog.
Right,
It might not know exactly what it is, but it knows it's not a cat.
right.
That's essentially what the autoencoder does with these boosted jets. It's trained on tons of simulated data, learning the typical patterns of known physics.
So when it sees a jet that doesn't fit the mold, that's our clue that something interesting is going on.
Exactly. That's when the alarm bells start ringing, and physicists know they might be onto something big.
This is blowing my mind.
Yeah.
But what I find even more fascinating is how this research takes things a step further with something called edge reconstruction.
Yes!
Can you tell us a little bit more about that?
Yeah, it's a new twist on the usual GNN approach. Remember those edges, the connections between particles?
Right, right.
This technique not only reconstructs the particles themselves, but also focuses on those relationships with incredible detail. It's like getting a high-resolution image of the jet's inner workings.
So instead of just seeing the dots, we're now seeing the lines connecting them with incredible clarity. That must be incredibly valuable for picking out those subtle anomalies.
Absolutely. It's like giving those physicists a magnifying glass to examine the subatomic world with unprecedented precision.
This is incredible. We're talking about potentially rewriting our understanding of the universe here. But how do we go from these reconstructed jets to actually making sense of what it all means?
That's where things get even wilder. Think about how we simplify complex information in our daily lives. Instead of listing every single ingredient, we just say chocolate chip cookie, right?
Or instead of describing every twist and turn, we just say, take the scenic route. I'm with you.
Yeah, it's all about finding a more compact, meaningful representation. And that's exactly what this GNN does with those reconstructed jets. It compresses all that complex data, those particles and their connections, into a lower dimensional space, kind of like a secret code.
A secret code hidden within the fabric of the universe. Okay, you've got my attention.
It's called latent space. Imagine taking a high-resolution picture and finding a way to represent it with just a handful of key parameters like brightness, contrast, those sorts of things. That's essentially what the GNN is doing, creating a simplified but incredibly valuable representation of the jet's essence.
So it's like distilling down all those complex interactions into a more manageable form, something physicists can actually get their heads around.
Exactly. And here's the best part. By analyzing these parameters, these coordinates within this latent space, physicists can start to unlock the hidden patterns, the telltale signs of new physics.
So instead of just spotting anomalies, they're looking for clues within those anomalies, patterns that might point towards something totally unexpected.
It's like learning a new language, the language of the universe itself. By studying how known particles cluster and move within this latent space, physicists can start to develop an intuition for what new particles might look like, how they might reveal themselves.
So it's not just about crunching numbers. It's about looking for those subtle whispers, those hints of something revolutionary hiding in plain sight. That must be an incredible feeling for a physicist.
Absolutely. And remember, this is just one example of the incredible potential of GNNs in particle physics. There are countless other ways these techniques could be applied, other mysteries waiting to be unraveled.
It really feels like we're on the verge of a new era of discovery, with GNNs leading the charge. But let's be realistic, no technology is perfect, right?
Yeah.
What are some of the challenges researchers are still facing in this field?
It does feel like we're on the cusp of something huge, but you're right. Every exciting new technology comes with its own set of hurdles. What are some of the big ones in this case?
It does feel like we're on the cusp of something huge, but you're right. Every exciting new technology comes with its own set of hurdles. What are some of the big ones in this case?
Well, one of the biggest challenges is that these GNN models require a colossal amount of data to really hit their stride. We're talking about simulating billions upon billions of particle collisions just to give these models enough information to learn from.
Wow, billions. That sounds like an astronomical amount of data.
It is. And it's not just about the quantity, but the quality of that data. Our simulations, while incredibly sophisticated, are still just approximations of the real world. There's always a risk that we miss some crucial detail, some nuance of these particle interactions that can make all the difference.
So it's like trying to teach a computer to recognize different types of birds, but only showing it pictures from a book. It might not recognize a bird in the wild with slightly different plumage.
That's a great way to put it. So there's this constant push and pull trying to create ever more realistic simulations while also developing GNN models that are more adaptable, less sensitive to those inevitable gaps between the digital world and the real one.
So it's a two-pronged challenge, improving the models themselves while also feeding them the richest, most accurate data possible.
Precisely. And of course, there's always that drive to innovate, to find even more elegant and effective ways to design these GNN architectures. Remember how this research introduced that groundbreaking edge reconstruction technique?
Oh, absolutely. It was like suddenly seeing the world in high definition.
It's a perfect example of the creativity and ingenuity that's pushing the boundaries of what these GNNs can achieve. This field is bursting with potential new types of GNN layers, ways to integrate our knowledge of physics directly into the models, even hybrid approaches that combine the strengths of GNNs with other machine learning techniques. It's a truly exciting time to be working in this area.
It sounds like there's never a dull moment.
No.
But that's what makes this research so captivating. It's not just about the technology. It's about pushing the very limits of human knowledge, unraveling the most fundamental mysteries of the universe.
And the most beautiful part is that you don't need to be a particle physicist with a PhD to appreciate the profound implications of this work.
Exactly. Whether you're a seasoned deep diver or just starting to explore these mind-blowing concepts, this research speaks to something deep within us, that innate human desire to understand where we come from, what we're made of, and what secrets the universe still holds.
Who knows what incredible discoveries await us just around the corner? One thing's for sure, with tools like GNNs at our disposal, the future of physics is looking brighter than ever.
Absolutely. And for all you deep divers out there, here's something to ponder as you go about your day. If you were a physicist armed with these cutting-edge GNNs, what cosmic mystery would you set your sights on solving? Let us know, because we're always eager to dive deeper into the mysteries that ignite your imagination. Until next time, keep exploring.